So in the past two videos you may have understood about and figure it out that how to segregate the data into the supervised and unsupervised learning, right? In the second video you might have understood that how do you actually represent your data by creating your own equation, okay, or coming up with your own conventional way of representing the data, right? So till the data part it is fine, but let's say that you are in production here and you are actually getting the data, so you always get the data in a very dirty manner, okay. You yourself are the sole responsible for making the model with a good accuracy, okay. So if you're not clean your data, if your data is not clean, then forget about that your model is getting or giving you a good accuracy, okay. So before you serving your data into the model, it is always a good practice that to check the little basic statistics, that whether your data is actually following the basic statistical norm or not, okay. And then this concept comes into picture, which is like EDA, which is like exploratory data analysis, okay. This is just a very simple basic way to understand it. Like for example, the mean and median, okay. So what does this mean and median will do? Mean and median will basically tell you about the imputation. So let's say that if you are actually getting the data something like this, you have a lot of features, feature 1, feature 2, you have feature 3, something like that, okay. And you will be having a data. In some part you will catch up the data which does not contain anything, okay, which is like null, which is containing the null value, okay. And you wanted to fill that null value, so how will you actually fill that null value? So let's say that out of 1,000 row, let's say that these two row is basically where the data is not like the data is unfulfilled, okay. So you have two way that you basically like take the mean of all the remaining element other than this two null value, and you basically take the mean of it, and you basically like uh, put the mean value into the null value, okay. So you basically try to just fulfill this gap, okay. So in this way you are actually imputing your data, right? The other way is like, for example, suppose, so this is the first way, okay, that imputation, okay. So you are actually handling imputation by finding out the mean and by replacing the mean with the null value, right? The other way is like, for example, suppose that if your feature is basically correlated, let's say that if the feature 1 and feature 2 are basically correlated, okay, there is a correlation between the feature and feature 2. So it is not always a good practice to like train your model with the lot of feature, okay. You yourself as a practitioner, it is your independent, it is your freedom that you can just like drain out this feature, okay. I hope you understand, okay. So if you let's say drain out this feature, let's say that if you have 100 feature, okay, and you drain out, and out of this 100 feature, let's say the 20 features are correlated, okay. So it means that the rest of the 80 features are basically unique, okay. So you may wanted to keep this 80 feature, okay, and you wanted to like drain out this 20 feature, okay. So that is why you wanted to find out the covariance, the correlation of these things, okay. So again, like the feature engineering, okay, the feature reduction, feature engineering, right? So these two, so this way you basically like wanted to clean your data. Again, the third part is, let's say that you wanted to like remove the outlier, okay. So when I say that actually removing the outlier, what does that mean? Removing the outlier means that suppose in your data, some data is actually like not fitting your data, okay. It is basically like it is coming from the different universe, okay. So it is not fitting your data at all. So you, as a practitioner, you wanted to remove that outlier, right? So before removing the outlier, so you should first identify that which of these are basically like which of the point is outlier, okay, so that I can basically remove it. So there is other way. So you want, so there is something called a box plot is also there, okay, where by plotting the box plot you will able to know that what percentage of your data is considered to be outlier. So you may wanted to drain that thing, okay. So again, so don't worry about all these things. So I will tell you a very one single line of a uh, this library which helps you to like do e- everything like on behalf of all these things, okay. So yeah, so just understand the basic concept. Again, then finding out the distribution. So you might have heard about the distribution, like the historical distribution, right? So what happens in the historical distribution is, let's say that you are actually in the class, right? And in the class, let's say there are many different age group, okay. There are many different age group, or let's say in a school there are many different age groups. So you find out that the age group between, let's say, 12 to 15 are having a good IQ, okay, based on a different age group, okay. And let's say the age group least, the age group which is more than that are actually having a very decrease in the IQ. Okay, so in this way you wanted to plot the histogram, okay, based on the very frequently used data. Okay, and like suppose if you wanted to use this histogram on a very continuous data, then you may come up with this distribution. So this distribution is basically held on a very continuous data, which is called the Gaussian distribution, right? So Gaussian distribution is like basically a smooth way of representing the histogram, right? So where each point will be having some kind of a, let's say, probability. So suppose if you wanted to represent it, so let's say into 0 to 1, so let's say that this point is actually having the higher probability compared to this one and compared to this one. So other than this actually represent a lot of things. So let me tell you like what. So what are the other things that you can actually like try to study it, right? So suppose that if your data, you somehow able to transform your let's say dirty data, right? Suppose if you wanted, so you actually use some kind of a transformation technique and you transform your data, and now your data is actually look in this distribution, right? Now this looks very clean, right? Why? Because first of all, the data is basically symmetric, okay, and the left part of the data and the right part of data is kind of equal, okay. And if you see this part, right, so this actually like contain the more 95% of the data, okay, which means like there is a 2.5% and there is a 2.5% are considered to be the outlier, okay, because this is actually having a very least probability, right, when it comes to the outlier part. And so my major focus would be into this reason, okay, other than these two reason, okay. So I can simply neglect that part. So this is the one way that I can actually study this Gaussian curve. So the other way of understanding this curve is like finding out the central limit theorem, okay. So you may understood about central limit theorem is something like mean, median and variance, okay, and then the standard deviation. So what mean is something like you wanted to find out the average, okay. Median is something like, suppose if you have a number, okay, so you wanted to find out the middle of that number, the middle index of that number, so from the median you would be able to get it, right? Then when it comes to variance, so what does variance will do? Variance is basically tells you about that the nearest data towards your mean, right? Suppose if actually having a very high variance, so it means that it is very nearer, so these data are basically succumb to very nearer to the mean data, okay. And suppose if the variance is low, then the data is basically far from the mean, okay. So this basically tells that that suppose, so this basically tells key, suppose if your data distribution is something like this, so you may be understanding that this region is having a very low variance compared to this region, okay. And when it comes to standard deviation, so what is this standard deviation do? Standard deviation is basically the distance. So let's say that, so suppose if I'm actually like taking this one, right, so this would come under my, let's say, the plus delta and let's say minus delta, okay. And suppose this is my mean, okay. So like this is my first first reason of the standard deviation, right? Now suppose if there is actually second reason, so this is actually the plus 2 delta and this is minus 2 delta, okay. So this is my second reason of the standard deviation, right? So something like that, okay. Now suppose that if I increase more data, okay, if I increase more data, can I expect that my curve will go down? Of course, right? So suppose that this X plot is basically like has been tested on, let's say, 10 million data, okay. Now suppose if I increase the 10 million data to 100 billion, like 100 million data, right? So can I expect that because the increase of the data, can I expect that my curve will now look more like this, right? Because my data has actually increased, so my height has actually decreased, right? Which means that my standard deviation is increased, right? Because compared to the earlier standard deviation, my new standard deviation has actually increased, right? So this is like a very good way of studying the data, of doing all kind of EDA, okay. So I hope you get it, right? Other thing is that it is always not true that you will get your data in a very like well fashioned normal distribution, okay. There may be a point where like your data something looks like this, right? So this is basically this skewness, okay. So like this is basically a good data, so this we can actually tell that this is my very balanced data, but this is not balanced data, okay. This is not balanced data. So why it is needed to convert any data into the balanced data, okay. So let's say that so how do I explain? Okay, yeah, let's say that you have actually having an age group, okay. And let's say from 10 years to 25 years to 35 years to 45 years, 50, 55, something like this, okay. And you maybe figure it out that up to the person who are actually lying in the age group of, let's say, 25 to 35 are having a very huge motivation towards work, okay. But by the time their age is actually increasing, so like they so their motivation of working for, let's say, 14 or 15 hours a day is kind of decreased, okay, because they have some other priorities, okay. So there may be data looks like something like this, right? Something like this, where like the tail of this curve, right, is basically towards the right, okay. So that is why it is basically right skew, right, where my tail is towards the right. Or and suppose the inverse of it would be looks like something like this, right, where my tail is towards the left, okay. So this is my left skew, okay. Now there might be possibility that the person belonging from 55 to 50 to 55 years of age are having some of these person are having a very good very good work ethic, right? So they are actually willing to put a lot of hours because they are more passionate, okay. Or maybe they are more their priority is more towards work compared to other thing, okay. You may take up the example of Warren Buffett, okay. I think at the age of 80 and 85, like him having involved in the work and going to the office, I think it's like it's very commendable, right? So yeah, there may be some person who are actually like working in this category, okay. So for them, having a right skew is very bad data representation. So that is the reason that you always wanted to like convert any of your representation of your data into some kind of a balanced way, okay, so that your data is looks something like more cleaner, okay, so that you could actually study it more practically, okay. So like how do you convert the data? So like you are actually using the Z transformation, right? So Z transformation is basically a statistical way to convert your data into this bell curve, okay. So let's say that if you have a data something like 100, 200, 20.2, like 15, 17, so these are basically my random data, okay. So what I will do is that I will just like pass it into the Z transformation method, and it will convert it into something like 0.2, 0.1, something like something like 0.8, uh, minus 2 minus 0.2, something like this, okay. So that so once you actually represented data, so the mean of this data would be 0, okay. Before earlier the mean may be, let's say, 12, okay, but now the mean is actually 0. So now the data is basically symmetrically arranged compared to this one, okay, because this you're actually getting the curve in a very right skew and left skew. You don't want that, okay. You want your data to be like represented in a very balanced and clean way, okay. That is why, so that is why these terms are very very needed, okay. So till now what you have understood about the mean, okay, the median, the variance, the standard deviation, okay, that what is basically the standard deviation part, the skewness, okay, the covariance. I think covariance is basically so covariance and correlation is like if your feature is basically correlated. So it's like suppose like the table of two, okay. So like the y-axis and then x-axis, okay. So these are basically the correlated, right, because let's say 2 times 1 is actually equals to 2, 2 times 2 is actually equals to 4, 2 times 3 is actually equals to 6, right. So these are basically, so these things are basically the correlated, right. So you wanted to find out the correlation factor, okay, and then this is basically the covariance, right. Normal distribution, does the Z score is basically your statistical test. The hypothesis testing is basically the p value, okay. Don't worry, I will come up with everything, okay, so that you would understood all these things. So yeah, so you knew about all these things. Then there is something called as population variance, sample variance, and standard deviation. So population variance is something like you wanted to find out the variance of the population data, okay. And similarly, out of the population data, right, so let's say that you have a something like something have a population data. So out of the population data, suppose I give you some sample data, let's say sample 1, let's say sample 2, okay. And I wanted to find out whether this sample is belonging from this population data or not. So what you will actually find it out, you wanted to find out, you will be finding out the mean, you will be finding out the standard deviation, you will be finding out the variance, and compare these things to the population mean and population variance and the population standard deviation. And you will be surprised to know that these things, if this sample if this is the sample of this population, then their mean, their standard deviation, their variance are much closer, okay. So yeah, these are just a very magical thing of statistics, I think. When it comes to the covariance part, so again, covariance is something like how so covariance is like so yeah, let's say if the data is actually falling into the same direction, okay. So basically it is covariance. So if let's say if your data is actually following something like this, okay, so it means that these data and these data is actually having a positive covariance value, okay. Now in order to find out that how these data are actually correlated, okay, and then what is the degree of correlation, right, like suppose if these two data is actually having a very positive covariance, right. So like at what degree I should be confirming that that these two are basically correlated. Okay, because again these two, if any of these data are actually following same positive trend, or let's say this trend, right, this is basically negative trend, or let's say some data is actually following some this trend, right. So if it is actually following it into the same quadrant, then you wanted to find out the correlation of it, right, the correlation part of it, that how these data are basically correlated. Okay, so this is basically the formula. Z score, again, this is basically like the Z transformation, where you wanted to transform your data into the bell curve, right, so that any dirty data is converted into your normal. Again, the skewness is important. Again, the sharpness and the flatness curve, the normal distribution, the sample mean. Again, these are basically the statistics tests. So yeah, there are very 4 or 5 major statistics tests that you need to learn. The first is something like t test, there is a Z test, there is an ANOVA test. Don't worry about it, you will get to know each and everything. Okay, so what is this and when you should do this statistical test? First of all, let's understand this, right, when you do this about the statistical set. So suppose that if I ask you, let's say, I'll give you one more example. Okay, so let me just figure it out, that which example should I tell you. Suppose you wanted to do some kind of a AB testing. Now what is AB testing, you might be asking, right? So suppose that you may have come up with the hypothesis that something like that, like for example, so you believe that you as a teacher, you believe that your student average score is, let's say, student average score is let's say 70. Okay, 70 marks, and 70 marks, and your strength is like 100. Okay, so for now you have just collected about the data of 100 student, and you have like come up with a solution key, like my average student score is like 70, like everyone should score around 70, right, and you wanted to find out the mean of it. Okay, you wanted to find out the standard deviation of it. Okay, and you already like, so you already find out the mean, you already find out the standard deviation, you already find out some other statistical test as well. Okay, now someone has given you p value. Now what is basically p value? So in statistics, p value is something called a significant value. Okay, significant value. What is actually significant value? Okay, so significant value is already determined or decided by your domain expertise, right? So let's say that if someone is actually like defined the p value is around, mm, let's say 0.25, something like that. Okay, now what does that mean? Suppose that you run the statistical test. Okay, and you are actually getting something like 0.1. Okay, and if it is actually less than your p value, okay, if it is actually less than your p value, it means that whatever assumption that you make, okay, over this 100 student, your assumption is completely true. Okay, which means that every student are getting around 70 marks. Okay, now suppose that if after like finding out the going through all these statistical tests, and suppose if your test is something like 0.1, which is like much greater than your given p value given by your domain expertise, what does that mean? It means that you basically failed to accept this hypothesis that your student are actually getting 70 marks, which means that you need more data, okay, to pass through this statistical test. Okay, so these are the tests that you wanted to like perform. Okay, and there are so many other things. So yeah, so there is a hypothesis testing rule, there is a chi-square test, there is an ANOVA test. Bayes theorem is very important. When I come across the name bias algorithm, I will discuss this part, right? So I think this is more than enough if you wanted to like perform your EDA operation on your data. So that data cleaning and then doing all these statistical performance is much needed for any machine learning practitioner. So if you have any doubt, just let me know. Okay, so I hope that and I think if you just understood about the 20% out of it, I think that is more than enough, because these are just the theory part, and when it comes to practical part, I'll show you that there is only one single library which will like do everything in a very completely deterministic way.